Hello there, and welcome back to Sleeping with Science Stories. This is where science meets peace, where the wonderful truths about the universe are told. If this is your first time finding this channel, please subscribe and turn on notifications so you don't miss the next journeys. And if you're already a member of this small family, thank you for coming back. Now, find yourself in the most comfortable position. Maybe you're lying in bed, head resting on a soft pillow. Maybe you're sitting with your back against the sofa or lying down on a rug. Wherever you are, let your body be fully supported by the surface beneath you. Let your shoulders relax. Let them fall down naturally, without tension. Let your neck relax. Let your jaw open slightly, no longer clenched tight. Tonight, we will explore together a fascinating topic: the wonderful truths about galaxies. When we look up at the night sky, we see twinkling stars. Most of those stars lie within our galaxy, the Milky Way. But if you have a telescope powerful enough and know where to look, you'll see other faint points of light, distant galaxies, each containing billions of stars of their own. And among those galaxies, there are objects so strange they challenge our imagination. Let's begin with one of the brightest and most violent phenomena in the universe: quasars. Quasar stands for quasi-stellar radio source. When astronomers first discovered them in the 1960s, they were puzzled. These objects looked like single stars, just small points of light in the sky, but they emitted enormous energy, far more than any star could produce. It took years of research before scientists understood what quasars really are. At the center of most large galaxies is a supermassive black hole. The mass of these black holes can be millions, even billions of times the mass of the Sun. In the Milky Way, the central black hole has a mass of about 4 million times the Sun. Currently, the black hole at the center of the Milky Way is quite quiet. It draws in some gas and dust from around it, but not much. But in some galaxies, especially distant galaxies we see as they existed billions of years ago, the central black hole is devouring matter at a terrifying rate. When a large amount of gas and dust falls toward a black hole, it doesn't fall straight in. Instead, it forms a spinning disk, an accretion disk, rotating around the black hole. Matter in this disk moves at extremely high speeds, nearly the speed of light in the regions closest to the black hole. As matter particles rub and collide with each other in the accretion disk, friction creates unbelievable temperatures, millions, even billions of degrees Celsius. At those temperatures, matter glows brilliantly. This light is mainly in the ultraviolet, X-ray, and even gamma-ray bands. And here's what's astonishing. A supermassive black hole actively eating matter can shine brighter than the entire galaxy containing it, brighter than hundreds of billions of stars combined. The black hole itself doesn't emit light. By definition, nothing escapes from a black hole. But the matter in the accretion disk, before it crosses the event horizon and falls into the black hole forever, shines with terrible intensity. That's a quasar, a galaxy with a central black hole eating so much that it shines brighter than all the stars in the galaxy. From a great distance, the entire galaxy appears to be just a brilliant point of light. The light from the tiny region around the black hole completely outshining the light from billions of stars. Quasars existed mainly in the early universe, billions of years ago. That was a time when galaxies were merging violently, colliding with each other, pushing large amounts of gas into the center, feeding the supermassive black holes. In the modern universe, most galaxies have stabilized more. The central black holes have consumed most of the nearby gas and are now starving. Quasars have become much rarer. But sometimes, when two galaxies collide in the present era, the process can reactivate black hole activity, creating a new burst of quasar brightness, though brief by cosmic timescales. And speaking of two colliding galaxies, that leads us to another strange phenomenon. Galaxies with two supermassive black holes orbiting each other. Imagine two galaxies, each with its own supermassive black hole at the center. When the two galaxies merge, a process that can take billions of years, eventually the two black holes will sink toward the center of the new merged galaxy. Initially, the two black holes might be thousands, even tens of thousands of light years apart. But gradually, over millions of years, they spiral closer together. Gravity and friction with surrounding gas and stars cause them to lose orbital energy, making them fall toward each other. Eventually, the two black holes can be just a few light years apart, or even closer, orbiting each other in a complex gravitational dance. This is called a supermassive black hole binary system. When two black holes orbit each other at close range, they emit gravitational waves, ripples in the very fabric of space and time. These waves carry away energy, causing the orbit of the two black holes to shrink progressively. Eventually, after perhaps millions or tens of millions more years in a tight binary state, the two black holes will merge in a violent event, emitting a strong pulse of gravitational waves detectable from billions of light years away. We've discovered several galaxies with strong signs of two active supermassive black holes. One famous example is galaxy OJ287. Astronomers believe this galaxy contains a huge supermassive black hole with a mass about 18 billion times the Sun and a smaller black hole, about 150 million times the Sun, orbiting around it. About every 12 years, the smaller black hole passes through the accretion disk of the larger black hole, creating a brightness flare observable from Earth. By tracking these flares over many decades, scientists can determine the orbit of the binary system and predict when the two black holes will merge, estimated to be about 10,000 years from now. But there are even stranger cases. Sometimes, a supermassive black hole doesn't lie at the center of the galaxy where it's supposed to be. An off-center black hole, or a kicked black hole. This can happen in several ways. One possibility is when three galaxies merge at the same time, a rare but possible event in crowded galaxy clusters. When three supermassive black holes interact, complex dynamics can kick one of them out of the center, sending it flying outward at speeds of thousands of kilometers per second. Another possibility involves gravitational waves. When two black holes merge, if they're not perfectly symmetrical, for example, one black hole is spinning rapidly and the other isn't, The gravitational waves emitted can be stronger in one direction than another. This creates a kick that can push the merged black hole out of the galaxy's center. Astronomers have found several candidates for off-center black holes. One example is in galaxy NGC 1600, where a supermassive black hole with a mass about 17 billion times the Sun, one of the largest black holes known, appears to lie about 2,200 light-years from the galaxy's center. Imagine a black hole weighing 17 billion times the Sun, racing through space, pulling with it a cloud of gas and stars. It's like a huge mobile city flying through the galaxy at speeds that could reach thousands of kilometers per second. Eventually, friction with gas and gravity from the rest of the galaxy will slow the black hole and pull it back toward the center. But this process can take billions of years. During that time, the galaxy has two centers: the geometric center, where most of the mass is concentrated, and the supermassive black hole wandering at another location. Now let's move to an even stranger type of galaxy, galaxies with almost no stars. You might think that the definition of a galaxy is a collection of stars, but there are galaxies that defy this definition. They have the size of a normal galaxy. They have the mass of a normal galaxy, but they have almost no stars. These galaxies are made primarily of dark matter. A famous example discovered in 2016 is called Dragonfly 44. This galaxy has a mass equivalent to the Milky Way, about 1 trillion times the mass of the Sun. But the number of stars in it is only about 1% of the stars in the Milky Way. 99.99% of Dragonfly 44's mass is dark matter. It's like a huge invisible skeleton with just a little visible flesh. How such a galaxy could form remains a mystery. One hypothesis is that during galaxy formation, some mechanism, perhaps winds from early massive stars, or energy from a supermassive black hole, blew most of the gas out of the galaxy before it could form many stars. Dark matter, because it doesn't interact with light or ordinary matter except through gravity, wasn't affected by these winds. It remained, holding the galaxy's structure, while ordinary matter was blown away. The result is a ghost galaxy, a huge structure nearly invisible, revealing its existence only through gravitational effects on surrounding light and matter. At the other end of the spectrum, we have galaxies forming stars at an insane rate. The Milky Way creates about 2 to 3 new stars each year. That's a steady, sustainable rate. But there are galaxies forming stars at a rate 1,000 times faster, 1,000 new stars per year, or even more. These galaxies are called starburst galaxies. Starbursts usually occur when two gas-rich galaxies collide. Gravitational forces and shock waves from the collision compress huge gas clouds, triggering mass collapse and star formation. In a starburst galaxy, the sky would be brilliant with young, hot blue stars. Star-forming regions glow with infrared light from dust heated by radiation from new stars. Supernovae explode constantly as short-lived massive stars die. A famous starburst galaxy is M82, also called the cigar galaxy because of its elongated shape. M82 is about 12 million light-years away and is forming stars at a rate about 10 times faster than the Milky Way. But there are far more extreme cases. Galaxy HFLS3, observed from when the universe was only 880 million years old, is forming stars at an estimated rate of about 2,000 stars per year, 1,000 times the Milky Way. This crazy star formation rate can't be sustained forever. The galaxy will quickly deplete its gas supply. After a few 100 million years, the starburst will end, leaving a galaxy with a large number of stars but very little gas to make more new stars. And at the largest scale, we have giant elliptical galaxies that lie at the centers of large galaxy clusters. These galaxies can be 100 times larger than the Milky Way in diameter and contain many times more stellar mass. Take, for example, IC1101, one of the largest known galaxies. Its diameter is about 6 million light-years, compared to about 100,000 light-years for the Milky Way. It contains an estimated 100 trillion stars, about 300 times the number of stars in the Milky Way. These giant galaxies formed over billions of years of mergers. They lie at cluster centers, where galaxy density is highest. Over time, they swallow galaxy after galaxy, growing like a snowball rolling downhill, accumulating mass. The supermassive black holes at the centers of these galaxies are correspondingly huge. C1101 may contain a black hole with a mass over 40 billion times the Sun. Most of the stars in these giant galaxies are old and red. They've exhausted most of their gas for making new stars. So although they contain a huge number of stars, they usually appear yellow or red in images, reflecting the old age of their stellar population. And finally, another strange phenomenon: galaxies that are just cold gas, with almost no stars. These objects blur the boundary between galaxies and intergalactic gas clouds. They have enough mass to be considered galaxies, perhaps from a few billion to tens of billions of times the mass of the Sun in hydrogen gas. But for some reason, this gas hasn't collapsed to form stars. One example is the Smith cloud, a huge gas cloud hurtling toward the Milky Way at about 240 kilometers per second. It contains enough gas to make about 2 million stars with the mass of the Sun. But currently, it has almost no stars. Astronomers believe the Smith cloud may be the remnant of a dwarf galaxy torn apart by the Milky Way in the past, or it may be gas blown out of the Milky Way hundreds of millions of years ago that is now returning. In about 30 million years, the Smith cloud will collide with the Milky Way's disk. This collision could trigger a new burst of star formation in the collision region. These phenomena, brilliant quasars, binary black holes orbiting each other, off-center black holes flying through space, ghost galaxies made of dark matter, starburst galaxies forming stars insanely, giant galaxies swallowing hundreds of other galaxies, and huge gas clouds that haven't formed stars, all show the rich and strange diversity of the universe. Each galaxy is unique. Each has its own history, its own structure, its own destiny. And when we observe them, we're looking into the past, because light takes time to travel through space. A galaxy 1 billion light-years away appears to us as it existed 1 billion years ago. The universe is a living museum of history. Every galaxy we observe is a window into a different moment in the past. When we look up at the night sky, everything seems quiet, motionless. The stars appear to stand still in their positions. The Milky Way stretches across the sky like a faint, unchanging band of light. But that impression of stillness is an illusion. Everything is moving. Stars are orbiting around the galactic center. The galaxy is rotating. And even right now, the Milky Way is eating another galaxy. That galaxy is called the Sagittarius Dwarf Elliptical Galaxy, or SAG-DEG for short. This is a small galaxy containing about a few tens of millions of stars, tiny compared to the hundreds of billions of stars in the Milky Way. It lies on the far side of our galactic center, in the direction of the constellation Sagittarius, and is being pulled into the Milky Way by gravity. Sagittarius Dwarf has orbited the Milky Way many times over billions of years. Each time it passes through, tidal forces from the Milky Way tear some stars away from it. These stars don't return to the dwarf galaxy, but instead begin orbiting the Milky Way as part of it. Over time, Sagittarius Dwarf has been stretched into a long stellar stream wrapping around the Milky Way like a tangled ribbon. Some estimates suggest this stellar stream may wrap around our galaxy multiple times, extending hundreds of thousands of light years. And the tiny dwarf galaxy originally is now just a remnant, a small fraction of its original mass, continuing to be torn apart with each orbit around the Milky Way. Eventually, in a few more billion years, it will completely disintegrate, and all its stars will become part of the Milky Way. This isn't a singular event. Sagittarius Dwarf is just one of many dwarf galaxies the Milky Way has been and is eating. When astronomers map the detailed positions and velocities of millions of stars in our galaxy, they discover many stellar streams, long bands of stars stretching across the sky, each band being the trace of a dwarf galaxy swallowed by the Milky Way. There's the Helmi Stream, the Monoceros Ring, the Orphan Stream, and many others. Each stellar stream is a story of a small galaxy that was torn apart and digested. Some stars in the Milky Way aren't native-born. They weren't born in this galaxy, but came from other galaxies, from places that no longer exist as separate entities. They are refugees, survivors from dead galaxies. And this process is still ongoing. Right now, gravity from the Milky Way is pulling stars from Sagittarius Dwarf, from the Large Magellanic Cloud, from other dwarf galaxies orbiting us. But it's not just the Milky Way acting on smaller galaxies. The entire Milky Way is also being affected by gravity from outside. Cosmic tidal forces are stretching the Milky Way. The Milky Way doesn't exist in a vacuum. It's part of the Local Group, a small cluster of about 80 galaxies bound together by gravity. The largest galaxy in this group is Andromeda, slightly larger than the Milky Way. The second largest galaxy is the Milky Way itself. The rest are much smaller dwarf galaxies. Gravitational force from Andromeda and other galaxies, plus forces from larger structures like the Virgo supercluster, create tidal forces stretching the Milky Way in different directions. These forces are very small compared to the internal gravity holding the Milky Way together, so they don't tear the galaxy apart, but they can subtly affect its shape, perhaps stretching the galactic disk, warping the spiral arms. And there's one particularly important tidal force acting on the Milky Way, the force from Andromeda Galaxy, because these two galaxies are moving toward each other. Andromeda is about 5 million light-years away and is moving toward the Milky Way at about 110 kilometers per second. That's very fast by human standards, but over the enormous distances of space, this process happens slowly. In about 4 billion years, about the same as Earth's current age, the two galaxies will begin colliding. But collision doesn't mean the stars will crash into each other. The distances between stars in a galaxy are very large compared to their sizes. When two galaxies pass through each other, most individual stars won't collide directly. They'll pass through the empty spaces between the other galaxy's stars. But the overall gravitational fields of the two galaxies will interact strongly. Tidal forces will stretch both galaxies. Spiral arms will be distorted. Some stars will be flung out into intergalactic space. The first collision won't be the end. After the two galaxies pass through each other, gravity will pull them back. They'll collide a second time, then perhaps a third. With each collision, the two galaxies lose orbital energy due to tidal forces and interactions with gas and stars. They slow down, their orbits growing tighter. Eventually, after a few billion years of repeated collisions, the two galaxies will merge completely into a single galaxy. This merged galaxy will probably no longer be a spiral. The collision process destroys the delicate spiral structure. Instead, the result will likely be an elliptical galaxy, with an elliptical or spherical shape, no spiral arms, no flat disk. This elliptical galaxy is sometimes jokingly called Milkometa or Milkdromeda by scientists, combining Milky Way and Andromeda. But what is the fate of the solar system in this event? Fortunately, the probability of the Sun, or any star in the solar system, colliding directly with a star from Andromeda is extremely low, nearly zero. The distances between stars are too great, but the solar system could be thrown into a different orbit. Currently, we lie about 26,000 light-years from the Milky Way's center, at a relatively safe position in the galactic disk. After the merger, the solar system could be thrown farther out, perhaps 50,000 or 100,000 light-years from the new galaxy's center. Or it could be thrown closer in. But Earth and the planets will continue orbiting the Sun as normal. The gravitational force between the Sun and the planets is much stronger than any tidal forces from the galaxy. Of course, by that time, 4 billion years later, life on Earth may have already ended for other reasons. The Sun is slowly becoming brighter over time as it ages. In about 1 billion years, Earth may have become too hot to sustain life as we know it. And in about 5 billion years, the Sun will become a red giant, swallowing the inner planets, including possibly Earth. But even if life on Earth ends, the atoms that make us up will still be there, part of the universe, perhaps becoming part of new planets, new stars, in the merged galaxy. The collision between the Milky Way and Andromeda isn't unique. Galaxies collide with each other regularly in the universe. It's an important part of how galaxies evolve. But sometimes, the result of a collision or interaction isn't a merger. Sometimes, a galaxy can be kicked out of its cluster. This can happen in large galaxy clusters, where many galaxies are moving at high speeds. When three galaxies interact at the same time, complex dynamics can push one of them out at very high speed. These galaxies are called runaway galaxies. They fly through intercluster space at thousands of kilometers per second, away from the cluster they once belonged to. A runaway galaxy may eventually escape the cluster completely and become a lonely galaxy in the vast space between clusters. Or it may slow down and eventually fall back into the cluster after billions of years. Galaxy merger processes produce different results depending on the size and type of the participating galaxies. When two large spiral galaxies of comparable size merge, the result is usually a smooth elliptical galaxy with no disk, no spiral arms. Elliptical galaxies contain mainly old, red stars, because most of the gas for making new stars has been consumed or heated to the point where it can't collapse to form stars. But during the merger process, before becoming elliptical, the galaxies can create beautiful temporary structures called tidal tails. When two galaxies pass close to each other, tidal forces stretch them. Some stars and gas are pulled out of the main galaxy, forming long streams extending into space. These streams can extend hundreds of thousands of light years. Images of merging galaxies with long tidal tails are often spectacular. There are the mice galaxies, with two long curved tails. There are the antennae galaxies, with two tidal tails looking like an insect's antennae. These tidal tails don't exist forever. Over billions of years, as the two galaxies merge completely, the stars in the tidal tails will fall back into the merged galaxy or disperse into intergalactic space. And when two galaxies merge, it's not just the stars interacting. The supermassive black holes at the center of each galaxy also gradually move toward each other. Initially, the two black holes might be tens of thousands of light years apart. But over time, dynamical friction with surrounding stars and gas slows them down and pulls them toward the merged galaxy's center. Eventually, the two black holes can be just a few light years apart, or even closer, orbiting each other in a binary system. And when they orbit each other at close range, they emit gravitational waves. Gravitational waves are ripples in the fabric of space and time, traveling at the speed of light. They were predicted by Einstein over 100 years ago, but were only directly detected for the first time in 2015 by the LIGO detectors. When two supermassive black holes orbit each other and eventually merge, they emit strong gravitational waves detectable from billions of light years away. These waves carry information about the masses and orbits of the black holes, allowing scientists to study these events even when they occurred in the distant past. So galaxies aren't isolated, motionless islands. They move, interact, collide, merge. They eat each other, they evolve over time, and the entire universe is a dynamic drama where galaxies are actors constantly changing, constantly evolving. Light is the primary means we use to explore the universe. Most of what we know about distant galaxies comes from the light they emit. Light that has traveled through space for millions, billions of years to reach us. But light doesn't simply travel in straight lines through empty space. It can be bent, stretched, obscured. And it's these transformations of light that reveal to us the deep secrets of the universe. Let's start with one of the most wonderful phenomena in astronomy: gravitational lensing. According to Einstein's general theory of relativity, mass bends space and time around it. One way to visualize this is to imagine a flat sheet of fabric representing space. When you place a heavy ball on the fabric, it creates a depression. That's how mass bends space. Light travels along the shortest path in space. But when space is curved by mass, the shortest path is no longer a straight line. Light will follow the curvature of space, like a marble rolling along the curve of the fabric. The result is that light from a distant galaxy can be bent when it passes near a massive object, like a galaxy cluster, lying between us and that galaxy. This creates an effect like a giant lens. The galaxy cluster acts like a gravitational lens, bending and magnifying light from the galaxy behind it. And this gravitational lensing allows us to see galaxies that without it, we would never be able to observe. Some galaxies are too far, too faint to detect with ordinary telescopes. The light from them is too weak. But when a galaxy cluster lies precisely between us and that distant galaxy, the lensing effect can magnify the distant galaxy's brightness by tens, even hundreds of times. Suddenly, the invisible galaxy becomes bright enough to detect. And not just brighter, its image is also distorted. Instead of a small point of light, we might see an elongated arc, or even a complete circle called an Einstein ring, if the alignment is perfect. And sometimes, light from a single galaxy can take multiple different paths around the lensing galaxy cluster. We see multiple images of the same galaxy at different positions in the sky, each image distorted in its own way. Astronomers have used gravitational lensing to discover some of the most distant and earliest galaxies known. Thanks to gravitational lensing from large galaxy clusters, we've seen galaxies that existed when the universe was only a few 100 million years old, just a small fraction compared to the current age of 13.8 billion years. These galaxies formed very early after the Big Bang, during a period called cosmic dawn, when the first stars began to light up and the first galaxies began to come together. The James Webb Space Telescope, launched in late 2021, has used gravitational lensing to discover some of the most distant galaxies ever observed. One of them, named JADS-GS-Z13-0, existed when the universe was only about 325 million years old. Light from this galaxy has traveled over 13.4 billion years to reach us. When we look at that galaxy, we're looking into the deep past, seeing the universe as it existed just a small fraction of its lifetime after it began. But there's something strange about light from distant galaxies. It doesn't look like light from nearby galaxies. When astronomers analyze light from a distant galaxy, they split it into different wavelengths, like a prism splitting white light into a rainbow. This creates a spectrum, showing the light intensity at each wavelength. In that spectrum, there are characteristic lines corresponding to specific chemical elements. Hydrogen creates lines at specific wavelengths. Oxygen, carbon, other elements do the same. These lines are like chemical fingerprints of the galaxy. But when astronomers look at the spectrum of a distant galaxy, they see that all these lines have shifted. They appear at longer wavelengths than expected. Blue light becomes green. Green becomes yellow. Yellow becomes red. Red becomes infrared. The entire spectrum has shifted toward the red, toward longer wavelengths. This is called redshift. Redshift occurs because the universe is expanding. As light travels through expanding space, its wavelength is stretched. Light that was originally ultraviolet, after billions of years traveling through expanding space, becomes visible light, or even infrared. The amount of redshift tells us how far the galaxy is from us and how long the light has traveled. The more redshift, the farther and more primordial the galaxy. Nearby galaxies have small redshift. Andromeda galaxy, 2.5 million light-years away, actually has a blue shift because it's moving toward us, not away. But distant galaxies have large redshift. Galaxy JADES-GS-Z13-0 I mentioned has a redshift of about 13, meaning the light's wavelength has been stretched by 14 times since it was emitted. And extremely distant galaxies are receding from us at speeds approaching the speed of light. Not because they're moving through space that fast, but because the space between us and them is expanding very rapidly. When space expands fast enough, the distance between 2 points can increase faster than the speed of light, even though nothing is actually moving through space faster than light. This is an important subtlety. Space can expand at any rate, and the light speed limit only applies to objects moving through space, not to space itself. Some galaxies are so far away that the light they emit today will never reach us. The space between us and them is expanding faster than light can cross. Those galaxies have crossed our cosmic event horizon and disappeared from observation forever. But light isn't just redshifted. Sometimes it's also completely blocked. Dust, tiny particles of carbon, silicon, and other elements can absorb and scatter visible light. When a galaxy contains a lot of dust, light from the stars inside can be blocked, making the galaxy faint or even invisible in visible light. These galaxies are sometimes called hidden galaxies, but although they're invisible in visible light, they still emit radiation at other wavelengths. Dust absorbs visible and ultraviolet light from stars, heats up, and then re-emits that energy as infrared radiation. So a galaxy can be faint or invisible in visible light, but brilliant in infrared. By observing at infrared wavelengths, astronomers can detect galaxies obscured by dust. And some galaxies emit strongly in X-rays, especially galaxies with strongly active supermassive black holes at their centers, or galaxies undergoing starbursts with many supernovae. X-rays are very high energy and can penetrate dust, so even a galaxy heavily covered by dust can still be detectable in X-rays. To truly understand a galaxy, astronomers need to observe it at many different wavelengths: visible light, infrared, ultraviolet, X-rays, even radio waves. Each wavelength reveals a different aspect of the galaxy. And sometimes, galaxies don't just emit light, they also shoot out matter. Some galaxies have jets shooting out from their centers, extending millions of light years into space. These jets are created by the supermassive black hole at the galaxy's center. When matter falls into the black hole, some of it doesn't fall straight in, but is ejected in two opposite directions, perpendicular to the accretion disk. The exact mechanism is still not fully understood, but it involves strong magnetic fields around the black hole. These magnetic fields can focus and accelerate charged particles, shooting them outward at speeds approaching the speed of light. These jets can extend incredibly far. A famous example is Galaxy M87. We talked about the supermassive black hole at this galaxy's center in the previous script. It was the first black hole directly photographed in 2019. M87 has a jet extending at least 5,000 light-years from the galaxy's center. This jet glows in visible light, X-rays, and radio waves. Particles in the jet move at speeds approaching the speed of light, but there are jets much longer. Galaxy 3 C236 has jets extending a total of about 15 million light-years, more than 150 times the diameter of the Milky Way. Imagine a structure extending 15 million light-years, created by a black hole at the center of a galaxy. It's like a giant sword cutting through the universe, illuminating intergalactic gas along its path. These jets carry enormous energy out of the galaxy, affecting the surrounding environment on extremely large scales. They can heat intergalactic gas, preventing it from collapsing to form new galaxies. They can trigger star formation in some regions by compressing gas. And these jets aren't static. They change over time as the black hole changes direction, or as black hole activity increases and decreases. Sometimes a jet can turn off for a while, then turn back on, creating lobes of older matter farther from the center. Some of the largest radio galaxies have complex structures with multiple lobes and jets at different angles, reflecting the long and complex history of central black hole activity. And when we observe these giant structures, we're not just seeing light. We see evidence of processes of energy, of interaction between the galaxy and its surrounding environment. Each galaxy is a source of light, but that light carries information. It tells us where the galaxy is, how long ago, what it's made of, how it's moving, how it's evolving. Light is bent by gravity, revealing invisible dark matter. Light is stretched by the expansion of the universe, showing us distance and time. Light is blocked by dust, but re-emitted at other wavelengths, allowing us to see through the veil. The universe is sending light to us from every direction, from every era, and by learning to read that light, we're learning to read the history of the universe. There's a profound secret about galaxies that took decades for scientists to discover. A secret that completely changed how we understand the universe. That secret is what we see is only a small part of what actually exists. Every galaxy we observe, with billions of twinkling stars, with glowing gas clouds, with all its brilliant beauty, only accounts for about 15% of that galaxy's total mass. The remaining 85% is something we can't see, something that doesn't emit light, something that doesn't absorb light, something that doesn't interact with light or ordinary matter in any way except through gravity. That something is called dark matter. And the story of how we discovered dark matter is one of the most fascinating stories in the history of science. It began in the 1970s with an astronomer named Vera Rubin. She was studying how spiral galaxies rotate. A spiral galaxy, like the Milky Way, rotates like a giant disk. Stars at different distances from the center orbit around that center at different speeds. And according to Newton's law of gravity, Rubin expected to see a specific pattern. In the solar system, planets near the Sun orbit faster than distant planets. Mercury orbits the Sun in 88 days. Earth takes 365 days. Neptune takes 165 years. The farther out, the slower. That's because gravitational force weakens with distance. Rubin expected the same with galaxies. Stars near the galactic center should rotate fast. More distant stars should rotate slower. And at the galaxy's edge, where very few stars remain, rotation speed should drop sharply. But when she measured the actual speeds of stars at different distances, she saw something completely unexpected. Rotation speed didn't decrease at the galaxy's edge. Instead, it remained nearly constant. Stars at the galaxy's edge, tens of thousands of light years from the center, rotated at nearly the same speed as stars closer to the center. This was strange. This couldn't happen if the galaxy's mass came only from visible stars and gas. There must be additional mass somewhere, mass we couldn't see, creating additional gravity to keep the edge stars rotating so fast. Rubin wasn't the first to notice this anomaly. In the 1930s, astronomer Fritz Zwicky found evidence for invisible matter when studying galaxy clusters. But Zwicky's work was largely ignored for decades. Rubin provided much clearer, more systematic evidence. She studied dozens of galaxies, and all showed the same pattern: flat rotation curves instead of declining ones. The only possible conclusion was, each galaxy is surrounded by a huge halo of invisible matter, a dark matter halo. This halo extends much farther than the disk of visible stars. If the Milky Way has a stellar disk extending about 100,000 light years, then the dark matter halo might extend 500,000 or even 1,000,000 light years. And this halo isn't a thin shell. It's a huge three-dimensional structure, possibly spherical or slightly flattened, containing most of the galaxy's mass. Imagine the Milky Way as a flat disk made of bright stars, floating in a huge, invisible sphere of dark matter. This sphere is 5 to 10 times larger than the stellar disk and weighs 6 times all the stars combined. We live inside this invisible sphere. Every second, billions of dark matter particles are passing through your body. They don't collide with the atoms in your body. They leave no trace. They just pass through, like ghosts through walls. But although dark matter doesn't interact with us directly, it interacts through gravity, and that gravity is extremely important. Without dark matter, galaxies like the Milky Way couldn't exist the way they do. Think about this. The Milky Way is rotating. The Sun is orbiting the galactic center at about 220 kilometers per second. That's extremely fast. At that speed, without enough gravity holding the Sun in, it would fly out of the galaxy into intergalactic space. Like when you spin a ball on a string. If you spin fast enough and let go, the ball flies away. The tension of the string is what keeps the ball spinning in a circle instead of flying straight out. For stars and galaxies, gravity plays the role of the string. It pulls stars toward the center, keeping them orbiting instead of flying outward. But the mass from the visible stars and gas isn't enough to provide the necessary gravity. At the actual speeds stars are rotating, especially at the galaxy's edge, they should fly outward. The galaxy should disintegrate, but it doesn't disintegrate, because dark matter provides the additional gravity needed. Dark matter is the invisible string holding the galaxy together, and not just individual galaxies. Galaxy clusters and superclusters, even larger structures, can only exist thanks to dark matter. Think about a galaxy cluster, a collection of hundreds or thousands of galaxies bound together by gravity. Galaxies in the cluster move at hundreds or thousands of kilometers per second. They're flying through the cluster at enormous speeds. If the cluster's mass came only from visible galaxies, gravity wouldn't be strong enough to hold them in. The galaxies would fly out of the cluster and disperse into space. But galaxy clusters remain stable. They've existed for billions of years. This can only happen if there's more mass than what we see. And in fact, when astronomers calculate the amount of mass needed to hold a galaxy cluster together, they find that dark matter must account for about 85% of the cluster's total mass. Only 15% is ordinary matter: stars, gas, dust. One way to see dark matter in galaxy clusters is through gravitational lensing that we discussed in the previous section. When light from distant galaxies passes through a galaxy cluster, it's bent by the cluster's gravity. The degree of bending tells us how much mass is in the cluster. By detailed mapping of the distorted images of background galaxies, astronomers can create a mass map of the cluster, showing where mass is distributed. And these maps reveal something clear. Mass isn't concentrated where visible galaxies are. There are vast regions with large mass, but very few or no visible galaxies. That's dark matter. A famous example is the bullet cluster we mentioned in the previous script. This is the result of two galaxy clusters colliding. Hot gas from the two clusters collided and slowed down, concentrating in the middle. But dark matter from the two clusters passed through without colliding, continuing forward. The result is a clear separation between where the visible gas is, in the middle, and where the largest mass is according to gravitational lensing maps, on both sides. Dark matter has separated from ordinary matter. This is one of the strongest pieces of evidence that dark matter is truly a separate component, not just an error in our theory of gravity. And at the largest scale, galaxy superclusters also are held together by dark matter. Superclusters are collections of many galaxy clusters. The Milky Way is part of the Virgo supercluster, containing over 100 galaxy clusters spread across about 110 million light-years, and the Virgo supercluster is part of Laniakea, an even larger superstructure containing over 100,000 galaxies. These huge structures can only form and be maintained thanks to dark matter. Dark matter creates the invisible skeleton that ordinary matter attaches to. In the early universe, a few 100 million years after the Big Bang, matter was distributed almost uniformly everywhere. There were tiny fluctuations in density. Some regions slightly denser, some slightly less dense. These fluctuations were very small, only a few parts in 100,000, but they were enough to start a process. In the slightly denser regions, gravity was slightly stronger. That region pulled in matter from around it, becoming even denser. Gravity grew stronger, pulling in even more matter. This is a self-reinforcing process. Regions that were initially slightly denser became increasingly denser, and regions initially slightly less dense became increasingly less dense as matter was pulled out of them. This is a gradual separation process. Matter gathered into filaments and nodes, leaving large, empty regions in between. Galaxies formed in the dense regions, along filaments, and at nodes. Very few galaxies formed in voids because there wasn't enough matter there, but there are some galaxies that exist in voids. These galaxies are very special and have a poetic name: cosmic hermits. A cosmic hermit is a galaxy lying deep inside a void, tens or hundreds of millions of light years from any other galaxy. It exists in near complete solitude. How can these galaxies exist there? There are a few possibilities. Some may have formed in rare density fluctuations within voids, tiny regions that randomly had enough matter to form a galaxy. Others may have been kicked into voids from nearby galaxy clusters through complex gravitational interactions. Just as a galaxy can be flung out of its cluster, a galaxy can be launched into a void and continue drifting in solitude. Living in a cosmic hermit galaxy would be a strange experience. If you looked up at the night sky from a planet in that galaxy, you'd see the stars of your own galaxy. But when looking through the most powerful telescope, you'd see very few other galaxies. The sky would be dark and empty to a frightening degree. You wouldn't know that there are billions of other galaxies out there, hiding at the void's edge, too far to see easily. You might think your galaxy is the only one in the universe, but most galaxies aren't that lonely. Most exist in groups, clusters, or along the filaments of the cosmic web. Our Milky Way isn't a cosmic hermit. We're part of a large galaxy community. First, we belong to the local group, a small cluster of about 80 galaxies, where the Milky Way and Andromeda are the two largest galaxies. But the local group is just a small part of a much larger structure, the Virgo supercluster. The Virgo supercluster contains over 100 galaxy clusters spread across about 110 million light-years. The largest cluster in this supercluster is the Virgo cluster, containing over 1,300 galaxies and located about 54 million light-years from us. Gravitational force from the Virgo cluster is pulling the local group toward it. We're falling into the Virgo cluster, though this process will take billions of years. But even the Virgo supercluster is just part of an even larger structure. In 2014, astronomers announced an astonishing discovery. They had mapped the motion of galaxies in a vast region around the Milky Way, tracking how they move not just due to the universe's expansion, but also due to gravitational forces from large mass structures. By analyzing these motions, they identified a huge superstructure that the Milky Way is part of. They named it Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains over 100,000 galaxies spread across about 520 million light-years. It includes the Virgo supercluster, the Hydra Centaurus supercluster, and several other superclusters, all bound together by gravity and common flow. At Laniakea's center, or near the center, is the Great Attractor, a region with extremely strong gravity that we mentioned in the previous script. All galaxies in Laniakea are being pulled toward this region. The Milky Way lies near Laniakea's edge. We're not at the center, not in any special position. We're just one galaxy among over 100,000 others, all moving together in a huge cosmic flow. And Laniakea is just one of many similar superstructures in the observable universe. There are thousands, perhaps tens of thousands of superstructures like Laniakea, each containing hundreds of thousands of galaxies. All these superstructures together form the cosmic web, a network extending throughout the observable universe with a total diameter of about 93 billion light-years. And what's astonishing is this structure isn't random. It has patterns, has organization. It's like a natural work of art created by gravity and time. When scientists simulate the formation of cosmic structure on computers, starting from tiny fluctuations in the early universe and letting gravity act over billions of years. The results they get look remarkably similar to what we observe in the real universe. These simulations produce filaments, nodes, voids. They create web-like structure. And when scientists compare simulations with actual observations, they match astoundingly. This gives us confidence that we understand, at least at a basic level, how the universe develops structure. From tiny quantum fluctuations in the first second to the huge cosmic web today, we can trace the entire process through theory and observation. And there's something strange about the cosmic web that some scientists have noticed. It has an astonishing similarity to neural networks in the brain. If you look at an image of the cosmic web and an image of connected neurons in the human brain, they look very similar. Both have network structure with filaments and nodes. Both have densely connected regions and empty spaces in between. Of course, the scales are completely different. A neural network spans a few centimeters. The cosmic web spans billions of light years. And the underlying mechanisms are also completely different. Electrochemistry in the brain, gravity in the universe. But the structural similarity suggests there may be common mathematical principles about how complex systems self-organize into networks. Perhaps it's a natural pattern that different systems, at different scales, tend to form. Or perhaps it's just an interesting random coincidence, a reminder that the universe is full of unexpected patterns and connections. Whatever the reason, the cosmic web is one of the most beautiful and impressive structures we've discovered. It shows that the universe isn't chaos, isn't random. It has order, has structure, has organization at the largest scale. And we tiny creatures on a small planet in an average galaxy have learned to see that structure. We've mapped the cosmic web through millions of galaxy observations. We've simulated its formation on computers. We've understood how it evolved from tiny fluctuations into today's huge structure. And every time we look at an image of the cosmic web, we're looking at a work of art created by gravity, time, and dark matter, a work spanning billions of light years and billions of years of time. The Milky Way is a tiny point in that big picture. One galaxy among over 100,000 in Laniakea, part of a filament in the huge cosmic web, a small node in the cosmic network. When astronomers first began classifying galaxies in the early 20th century, they thought there were three basic types: spiral galaxies, like the Milky Way, elliptical egg-shaped galaxies, and irregular galaxies with messy shapes. But as telescopes became more powerful and we observed more galaxies, we realized the universe is much more creative than those three simple categories. There are galaxies with strange shapes, incredible structures, and properties that challenge all our understanding. These galaxies are exceptions, special cases, but they teach us a lot about the processes that can occur in the universe. Let's start with one of the strangest types of galaxies: polar ring galaxies. Imagine a normal spiral galaxy with a flat disk of stars rotating around the center, like the Milky Way. Now imagine a ring of stars and gas rotating perpendicular to that disk, like a ring around the planet Saturn, but at galaxy scale. That's a polar ring galaxy. This ring isn't small. It can contain billions of stars and extend tens of thousands of light years, and it rotates in a plane completely different from the galaxy's main disk. How can such a strange structure form? The leading hypothesis is that the polar ring is created when a large galaxy tears apart and swallows a smaller galaxy. If the smaller galaxy approaches at a specific angle, not from the disk plane but from above or below, matter from it can be pulled out into a ring, rotating perpendicular to the main disk. Or in some cases, the ring may be formed from gas pulled from a nearby passing galaxy. Tidal forces pull gas out of that galaxy, and this gas falls into the larger galaxy in a polar orbit. A famous example is Hoag's object, though this is a slightly different type. Hoag's object has a nearly perfectly spherical central core surrounded by a nearly perfectly circular ring of stars, with a dark gap between the core and ring. When viewed through a telescope, it looks like a giant eye staring from space. A yellow core at the center, acting as the pupil, surrounded by a blue ring of young stars. Hoag's object was discovered in 1950, and for decades, astronomers debated how it could have formed. Some argued it was the result of an extremely special galaxy collision. Others proposed different mechanisms. To this day, there's still no complete consensus. But most scientists believe ring galaxies, like Hoag's object, all involve galaxy collisions or interactions in some way. And speaking of collisions, that brings us to another strange type of galaxy, ring galaxies, sometimes jokingly called cosmic donuts. These galaxies are created by a very specific type of collision called a bullseye collision. Imagine a large, flat, spiral galaxy like a disk. Now imagine a smaller galaxy plunging straight through the center of that disk, like a bullet through a target. As the smaller galaxy passes through, it creates a shock wave in the larger galaxy's disk, like when you drop a stone into a still pond, creating ripples spreading out from the impact point. This shock wave spreads outward from the center, compressing gas and triggering violent star formation as it passes. The result is a bright ring of young blue stars expanding outward from the galaxy's center. At the center, where the collision occurred, there may be a small remaining core of the original galaxy, and between the core and ring is a relatively dark gap, where the shock wave has passed and left few stars. The result looks like a giant donut made of stars, a bright ring with a hole in the middle. A famous example is the Cartwheel Galaxy. It lies about 500 million light-years away and has a diameter of about 150,000 light-years, slightly larger than the Milky Way. The Cartwheel Galaxy has a brilliant blue outer ring with a diameter of about 150,000 light-years, where millions of young stars are being born. Inside this ring is a darker region, and at the center is a small core. Astronomers believe that about 200 million years ago, a smaller galaxy plunged through the center of a large spiral galaxy, creating a shock wave that has expanded outward and formed the ring we see today. The smaller galaxy that caused the collision may still be there, moving away after passing through. In fact, astronomers have identified two small galaxies near the Cartwheel Galaxy, one of which may be the culprit, and the shock wave is still continuing to spread outward. The ring is expanding at about 300 kilometers per second. In millions of years to come, it will continue to grow, creating more stars as it passes through new gas regions. Eventually, after a few 100 million more years, the shock wave will weaken and dissipate. The Cartwheel Galaxy may slowly restructure into a more normal spiral or elliptical galaxy. But for now, it's a beautiful example of a galaxy undergoing dramatic transformation. Now, let's move to a completely different type of galaxy, ultra-diffuse galaxies, or UDGs for short. These galaxies challenge our intuition about what a galaxy should look like. Most galaxies have a fairly consistent relationship between size and brightness. A large galaxy usually contains many stars and is therefore brighter. A small galaxy contains fewer stars and is fainter. But UDGs break this rule. They have the size of a large galaxy, perhaps spanning 50,000 or even 100,000 light years, equivalent to the Milky Way, but they only contain a small fraction of the number of stars. While the Milky Way has about 200 to 400 billion stars, a typical UDG might have only a few hundred million or a few billion stars. With so few stars spread across a large area, their surface brightness is extremely low. In other words, they're very faint. They're like galaxy ghosts, having size but nearly invisible. For decades, astronomers may have looked through these galaxies without recognizing they were there because they blend into the background sky. Only when observation techniques improved in recent years did we begin discovering them in large numbers. And it turns out they're not rare. There may be thousands or even tens of thousands of UDGs in large galaxy clusters. They may be one of the most common types of galaxies, just that we can't see them easily. How these galaxies could form remains a mystery. One hypothesis is they started as normal galaxies, but then lost most of their gas due to interactions with the cluster environment. Hot gas in the cluster can strip gas from the galaxy as it moves through, a process called ram pressure stripping. Without gas, the galaxy can't make more new stars. Existing stars continue to live and die, but there are no replacement stars. Over billions of years, the number of stars decreases, and the galaxy becomes fainter and fainter. Another hypothesis is that UDGs form in rapidly rotating dark matter halos. Rapid rotation can spread gas over a large area, making the density so low that stars form very slowly. The result is a large galaxy, but with very few stars. Some UDGs have other strange properties. For example, a UDG named Dragonfly 44 that we mentioned in the previous script has an unusually high number of globular clusters. Globular clusters are tight collections of hundreds of thousands of old stars. The Milky Way has about 200 globular clusters. Dragonfly 44, despite having far fewer stars than the Milky Way, has about 100 globular clusters, an unusually high ratio compared to the total number of stars. This suggests Dragonfly 44 may have once been a much larger galaxy and lost most of its stars over time, leaving only the globular clusters, the most resilient structures. And at the other end of the size spectrum, we have ultra-compact dwarfs, or UCDs for short. These galaxies are the complete opposite of UDGs. They're extremely small, perhaps only a few hundred light years in diameter, thousands of times smaller than the Milky Way, but contain tens of millions or even hundreds of millions of stars packed tightly into that tiny space. Star density in a UCD can be hundreds or thousands of times higher than the average star density in the Milky Way. Imagine living on a planet in a UCD. When you look up at the night sky, you'd see tens of thousands of stars brighter than Venus appears to us. The sky would be brilliant with starlight. It might never truly be dark. And the distances between stars would be much smaller than here. In the Milky Way, the nearest star to the Sun is Proxima Centauri, about 4.2 light-years away. In a UCD, the nearest star might be just a few light months, or even a few light weeks away. Astronomers believe most UCCDs are remnants of larger galaxies that were torn apart. When a small galaxy moves through a large galaxy cluster, tidal forces from the cluster can strip the outer layers of the galaxy, leaving only the dense central core. This core, now an independent galaxy, is a UCD, an extremely compact, dense dwarf galaxy that is the surviving part of something once much larger. Some UCDs have supermassive black holes at their centers. Another sign they were once larger galaxies, since large galaxies usually have supermassive black holes, while normal dwarf galaxies usually don't. And there's one other strange type of galaxy worth mentioning: irregular galaxies. This isn't a homogeneous group. Irregular really means doesn't fit the other categories. They're not neat spirals. They're not smooth ellipticals. They're warped, messy, chaotic. Some irregular galaxies are small and faint. The Large Magellanic Cloud and Small Magellanic Cloud, two satellite galaxies of the Milky Way visible from the southern hemisphere, are classified as irregular. These galaxies have some structure. There are star-forming regions. There are gas clouds, but no overall clear shape. They look like fragmented star clouds. Some irregular galaxies are larger and more dramatic. They may be the result of ongoing galaxy collisions. When two galaxies collide, before they merge completely, they go through a chaotic phase where structure is torn apart. Spiral arms are destroyed, and the result is a mess of stars, gas, and dust. The Antennae galaxy, which we mentioned earlier with its long tidal tails, is an example of an irregular galaxy created by an ongoing collision. All these strange galaxy types, polar ring galaxies with rings rotating perpendicular, ring galaxies like donuts created by bullseye collisions, ultra-diffuse galaxies, large but faint like ghosts, ultra-compact dwarfs, tiny but incredibly dense, and irregular galaxies warped and chaotic, all remind us that the universe is far more creative than we can imagine. Each type of strange galaxy is a natural laboratory showing us what can happen under extreme or unusual conditions. They challenge our models, expand our understanding, and remind us that there's always more to learn. And perhaps most wonderful is that we're still discovering. With each new telescope, with each new sky survey, we find stranger types of galaxies, more surprising structures. The universe is still full of mysteries and surprises, and that's part of its beauty. When we look at distant galaxies, we're not just looking across space. We're looking across time. Light takes time to travel. Light from a galaxy 1 billion light-years away has traveled for 1 billion years to reach us. When we see that galaxy, we're seeing it as it existed 1 billion years ago, not as it exists now. The farther we look, the further back in time we look. And with the most powerful telescopes, we can see galaxies that existed when the universe was still very young, just a few 100 million years after the Big Bang. These are the most primordial galaxies, the first galaxies to form after the universe began, and they're very different from the galaxies we see in the modern universe. The James Webb Space Telescope, launched in late 2021 and beginning operations in mid-2022, was designed specifically to observe these primordial galaxies. And it hasn't disappointed us. In its first months of operation, James Webb discovered dozens of galaxies that existed when the universe was only 200 to 500 million years old. Some even earlier. There's evidence for galaxies forming just 200 million years after the Big Bang. To put this in context, if you compressed the entire 13.8 billion year history of the universe into 1 year, these galaxies formed in the first few days of January. They are the first galaxies, the first structures of light to ignite in the darkness. Because the universe before that, in the first few 100 million years, was truly dark. This period is called the Dark Ages. After the cosmic microwave background radiation was released, about 380,000 years after the Big Bang, the universe contained mainly neutral hydrogen and helium gas. No stars had been lit. No galaxies had formed. Only cold gas drifting slowly in darkness. The CMB provided a faint light, but as the universe expanded, this light was stretched into longer and longer wavelengths, becoming weaker and weaker. After a few million years, it became too weak to meaningfully illuminate anything, and so the universe sank into darkness, a dark period lasting perhaps a few 100 million years. But in that darkness, the seeds of change were quietly growing. Dark matter, unaffected by light or gas, had begun gathering right after the Big Bang. Over millions of years, it formed halos, dense structures of dark matter spread throughout the universe, and hydrogen and helium gas, pulled by gravity from these halos, began falling into them. Gas gathered in the gravitational wells created by dark matter. As gas gathered, it heated up. Density increased. And at a magical moment, at the centers of the densest gas clouds, temperature reached about 10 million Kelvin, hot enough for fusion reactions to begin. The first stars ignited. This is cosmic dawn. Cosmic dawn. The moment when light first broke through the darkness of the Dark Ages. These first stars, as we discussed in the previous script, may have been very massive, tens or hundreds of times the mass of the Sun. They lived briefly but burned brilliantly, emitting strong ultraviolet light. This ultraviolet light had an important effect. It ionized the surrounding hydrogen gas. A neutral hydrogen atom, when absorbing a sufficiently energetic ultraviolet photon, loses its electron and becomes ionized, a single proton. This process, called reionization, created bubbles of plasma around each star and each group of stars. Initially, these bubbles were small and isolated, but as more stars formed, the bubbles grew and began merging. Over hundreds of millions of years, these bubbles spread, and eventually they merged completely, ionizing all the gas in the universe. This phase was completed about 1 billion years after the Big Bang. Since then, most hydrogen in the universe has been ionized. We're living in a reionized universe. But the first stars didn't exist alone for long. They quickly assembled into groups, and those groups became the first galaxies. The first galaxies were very different from the Milky Way. They were tiny, perhaps just a few million or a few tens of millions of stars, compared to hundreds of billions in the Milky Way. Their mass might be only 1,000th or 1,000,000th of the Milky Way's mass. They were fragmented, with no clear shape, no neat spiral disk, no smooth elliptical structure, just chaotic clumps of stars and gas. And they were forming stars at a frantic rate relative to their size. Though small, they could be forming stars at rates many times higher than the modern Milky Way per unit mass. Why? Because gas in the early universe was still primordial, not yet enriched by heavy elements from previous stellar generations. And primordial gas tends to gather and form stars more efficiently. Moreover, primordial galaxies contained much more gas relative to stars. Perhaps 90% or more of the ordinary matter mass in a primordial galaxy was gas. Only 10% was stars. This is very different from modern galaxies, where the ratio is usually more balanced or even tilted toward stars. And these tiny, fragmented galaxies didn't exist alone. They were constantly colliding with each other. The early universe was much smaller than the modern universe. Everything was closer together. Galaxies were packed more tightly. Collisions happened frequently, perhaps every few tens or few 100 million years for a typical galaxy. When two small galaxies collided, they usually merged quickly, forming a slightly larger galaxy. This new galaxy could then collide with another galaxy, growing even more. Over billions of years, the initially tiny galaxies gradually merged and grew into larger galaxies, and eventually into giant galaxies like the Milky Way. This is called the hierarchical model of galaxy formation. Small structures form first, then merge into larger structures, then even larger in a bottom-up process. And in this collision and merger process, many things happened. Each collision triggered a new burst of star formation when gas from the two galaxies collided and was compressed. These starbursts created millions of stars in a short period. Massive short-lived stars exploded as supernovae, enriching the surrounding gas with heavy elements, carbon, oxygen, iron, and other elements created in stellar cores. Over time, gas in galaxies became more metal-rich. In astronomical terms, metals means any element heavier than helium. Each stellar generation enriched the gas a little more, and black holes at galaxy centers merged with each other, forming larger black holes. Over billions of years and hundreds of mergers, black holes that initially might be just a few hundred or few thousand times the sun's mass grew into supermassive black holes, millions or billions of times the sun's mass that we see at the centers of large galaxies today. But there's a mystery that astronomers are still trying to solve. When James Webb began observing the most distant, most primordial galaxies, it discovered something unexpected. Some of these galaxies are larger and more mature than predicted. According to theoretical models, very primordial galaxies should be small, fragmented, chaotic. But some galaxies James Webb observed, existing just a few 100 million years after the Big Bang, already had fairly clear disk structure, already contained billions of stars, already had supermassive black holes at their centers. How could these galaxies have grown so quickly? How could they have already accumulated so many stars and organized into structure in such a short time? This is an open question. Perhaps our models need adjustment. Perhaps star formation in the early universe was more efficient than we thought. Perhaps dark matter halos grew faster than predicted. Or perhaps there are processes we don't fully understand yet. But that's the beauty of science. Each new observation can challenge what we thought we knew. Each unexpected discovery opens new questions, new research directions. And when we look at these primordial galaxies, we're looking at our own roots. The Milky Way didn't begin as a large, neat spiral galaxy. It began as one of those tiny, fragmented galaxies billions of years ago. Through hundreds of mergers, through billions of years of accumulating gas and making stars, it grew into the galaxy we see today. And that process is still ongoing. As we said, the Milky Way is still eating smaller dwarf galaxies. It's still growing, still evolving. In another 4 billion years, when it merges with Andromeda, it will undergo another major transformation, perhaps becoming a giant elliptical galaxy. So when we look into the universe's deep past, we're not just looking at alien galaxies. We're looking at our own ancestors. We're looking at the Milky Way as it might have looked in the distant past. And that brings a sense of deep connection. We're part of a long story, an evolutionary process spanning billions of years, from the first tiny galaxies to today's huge structures. The Milky Way is our home. It's the galaxy containing the solar system, containing Earth, containing everything we've ever known. But though we live in it, there's much about our galaxy that remains mysterious and astonishing. Let's start with a basic but easily forgotten fact. We're moving. The Sun, along with the entire solar system, is orbiting around the Milky Way's center. We lie about 26,000 light-years from the center, at a fairly distant position from the core, but not at the outermost edge. And we're moving at about 220 kilometers per second. That's 792,000 kilometers per hour. This enormous speed is much faster than Earth's speed orbiting the Sun, which is only about 30 kilometers per second. But even at such high speed, it takes a very long time to complete one orbit around the galaxy. One complete orbit, one cosmic year, takes about 225 to 250 million Earth years. Let that number sink in a bit. 225 million years. The last time the solar system was at its current position in its orbit, dinosaurs had just begun appearing on Earth. That was the Triassic period, when the first giant reptiles began dominating the planet. Since then, the solar system has traveled nearly one complete circle around the galaxy. And during that time, dinosaurs evolved, dominated Earth for over 160 million years, then went extinct. Mammals arose, and finally, humans appeared. The entire history of humanity, from the most ancient ancestors to now, accounts for only a very small part of one galactic orbit. If a cosmic year is 225 million years, then all of Homo sapiens, existing about 300,000 years, accounts for only about 0.13% of one orbit. We are very young creatures on a planet slowly orbiting an ancient galaxy, and the Milky Way itself is very old. Its age is estimated at about 13.6 billion years, only slightly younger than the universe, which is 13.8 billion years. The Milky Way has existed almost since the beginning, but not all parts of the Milky Way are the same age. Our galaxy has layered structure. There's a flat disk containing most of the young and middle-aged stars, including the Sun. There's a bulge at the center, containing older stars packed tightly. And there's a vast spherical halo surrounding the entire galaxy, containing the oldest stars. Stars in the halo are the most ancient stars in the Milky Way. Some are up to 13 billion years old or more, nearly as old as the universe. They formed in the galaxy's primordial phase, perhaps in the first few 100 million years. These stars have a special chemical characteristic. They're metal poor. In astronomical terms, metals means any element heavier than helium. Halo stars have very little carbon, oxygen, iron, and other heavy elements. Why? Because they formed from nearly primordial gas. Gas not yet much enriched by previous stellar generations. They belong to very early stellar generations, perhaps the second or third generation after the universe's first stars. In contrast, stars in the disk, including the Sun, are much younger and more metal-rich. The Sun is about 4.6 billion years old, only about a third the galaxy's age, and it contains a significant amount of heavy elements inherited from many previous stellar generations that lived, died, and enriched the interstellar gas. This difference in age and chemical composition tells us a story about the Milky Way's history. The halo formed first, in the chaotic period when the galaxy was still growing, through many mergers with smaller galaxies. Stars formed rapidly in those chaotic conditions, and they keep random orbits, not following a neat disk plane. The disk formed later, when the galaxy had stabilized more. Gas fell toward the galaxy's center, was flattened by rotation, and formed a thin disk. New stars continued forming in this disk to this day, creating the young blue stars we see in spiral arms. But there's something strange about stars in the Milky Way. Not all are native-born. When astronomers analyze the chemical composition and orbits of millions of stars in the galaxy, they discover that some stars have different properties. They move in strange directions. They have chemical compositions that don't match surrounding stars. These stars weren't born in the Milky Way. They came from other galaxies that were swallowed by the Milky Way in the past. We talked about how the Milky Way is eating Sagittarius dwarf right now, but that's not the first time. The Milky Way has swallowed many other dwarf galaxies in the past. In 2018, astronomers announced an astonishing discovery based on data from the European Space Agency's Gaia satellite. They identified a large group of stars in the Milky Way's halo with similar orbits and chemical composition, suggesting they had a common origin. They concluded these stars are remnants of a large dwarf galaxy that merged with the Milky Way about 10 billion years ago. They named this ancient galaxy Gaia Enceladus, or simply the Sausage Galaxy, because of the elongated shape of the stellar orbits. Gaia Enceladus may have had a mass about a quarter or a fifth of the Milky Way's mass at the time of merger. That was a major collision, possibly the largest in the Milky Way's history. That collision left traces. Tens of millions of stars in our halo today originated from Gaia Enceladus. They're refugees from a dead galaxy, now citizens of the Milky Way. And there are other remnants. The Helmi stream, a long stellar stream, is the remnant of another dwarf galaxy swallowed. There are also streams from other galaxies, each stream telling the story of an ancient merger. In total, Scientists estimate that perhaps 10% to 20% of stars in the Milky Way originated from other galaxies. 1 in every 5 or 10 stars you see in the night sky may have been born in another galaxy and then absorbed by the Milky Way. That's a beautiful reflection. Even in our home galaxy, there are immigrants from distant places, survivors from lost worlds. And this process is still ongoing. The Milky Way isn't just swallowing Sagittarius Dwarf. It's also interacting with many other satellite galaxies. Satellite galaxies are smaller galaxies orbiting a larger galaxy, like moons orbiting a planet. The Milky Way has over 50 known satellite galaxies, and there may be many more undiscovered. The 2 largest and most visible satellite galaxies are the Large Magellanic Cloud and Small Magellanic Cloud. They're visible to the naked eye from the southern hemisphere as faint bright clouds in the sky. The Large Magellanic Cloud contains about 20 billion stars and lies about 160,000 light-years away. The Small Magellanic Cloud is smaller, with about 3 billion stars and about 200,000 light-years away. Both these clouds are orbiting the Milky Way, and in the distant future, they may be completely absorbed into our galaxy. But most of the Milky Way's satellite galaxies are much smaller and extremely faint. These galaxies, called ultra-faint dwarf galaxies, may contain only a few thousand or a few tens of thousands of stars. Some have only a few hundred stars. Their total brightness may be only equal to a single bright star. They're extremely difficult to detect. For decades, we only knew of a few satellite galaxies of the Milky Way. But as sky surveys became deeper and more comprehensive in the 2000s and 2010s, we began discovering more and more ultra-faint dwarf galaxies. Some have names like Segway 1, Segway 2, Willman 1, Boötes 1, named after the surveys or constellations where they were found. They're so faint they can only be detected by complex statistical techniques, searching for small concentrations of stars with similar motion and distance. These ultra-faint dwarf galaxies are important for several reasons. First, they're the most primordial galaxies still existing. They formed very early and then hardly changed. They're living fossils, showing us what galaxies looked like in the early universe. Second, they have extremely high ratios of dark matter to ordinary matter. Some ultra-faint dwarf galaxies may be 99.9% dark matter, only 0.1% stars. They're the most dark matter-dominated objects known, making them perfect laboratories for studying dark matter's properties. Third, their number can tell us about dark matter's nature. Different dark matter models predict different numbers of satellite galaxies. By counting them, we can test these models. Currently, there's a problem called the missing satellites problem. Simulations based on the standard cold dark matter model predict the Milky Way should have thousands of satellite galaxies, but we only observe a few dozen. Perhaps many satellite galaxies are too faint to detect, even with current technology. Or perhaps the dark matter model needs adjustment. This is an open question in astronomy, and there's one final astonishing fact about the Milky Way. We still don't know exactly what it looks like from outside. We're in the galaxy, buried in the disk of stars and dust. We can't fly out and take a panoramic photo. Everything we know about the Milky Way's overall structure comes from carefully mapping the positions and velocities of millions of individual stars, then piecing them together to create a bigger picture. We know the Milky Way is a barred spiral galaxy with a bar at the center. This bar is a dense structure of stars extending through the galaxy's center, and spiral arms begin from both ends of the bar. But we don't know exactly the number of spiral arms. It could be 2 main arms with some minor arms. It could be 4 arms. Different studies give slightly different results. We don't know exactly what the Milky Way would look like if viewed from outside. We can photograph thousands of other galaxies, but our own galaxy remains mysterious in many aspects. That's a reminder of our position. We're not outside observers looking into the universe from afar. We're part of it, inside it, limited by our perspective. We've traveled through the deep past of galaxies, from the first stars lighting in darkness to today's huge structure of the cosmic web. But now, let's turn our gaze forward. Let's reflect on the future of galaxies, on the fate of the universe in unimaginably distant times. And that future, according to what we understand about cosmic physics, has a truth both sad and beautiful. The universe we can see today won't exist forever. This doesn't mean galaxies will literally disappear. They'll still be there, still exist, still contain their stars. But they'll disappear from our view, one galaxy after another, as the space between us and them expands faster than light can cross. We've talked about dark energy, the mysterious force making the universe expand faster and faster. And if dark energy continues as it is now, unchanging over time, then the fate of the observable universe is already predetermined. The most distant galaxies we can see today, galaxies billions of light years away, are receding from us at speeds approaching the speed of light due to space's expansion. And some have already crossed the cosmic event horizon, the point beyond which light never reaches us, no matter how long we wait. Every second, some galaxies cross that horizon and disappear from observation forever. Not because they're destroyed, but simply because the space between them and us is expanding faster than light can travel. In 1 trillion years, a number so distant it's hard to grasp, but try to imagine, most galaxies we see today will have disappeared from view. Galaxies in the Virgo supercluster will no longer be visible. Laniakea, the superstructure containing over 100,000 galaxies that we're part of, will disintegrate as most member galaxies recede far enough to cross the event horizon. Distant galaxy clusters, individual galaxies in the far regions of the observable universe, all will disappear, one after another, like stars dimming in the sky, and finally, only the local group will remain. The local group is the small cluster of about 80 galaxies that the Milky Way is a member of. It includes the Milky Way, Andromeda Galaxy, Triangulum Galaxy, and dozens of much smaller dwarf galaxies. These galaxies are close enough together, and gravity between them is strong enough to overcome space's expansion. They're bound together by gravity and won't be separated by dark energy. In fact, as we know, the Milky Way and Andromeda are moving toward each other. In about 4 billion years, they'll begin merging. The merger process will take a few more billion years, with multiple collisions, until finally they become a single galaxy, perhaps a giant elliptical galaxy some people jokingly call Milky Way. Triangulum Galaxy, the third largest galaxy in the local group, may also join this merger process, and smaller dwarf galaxies may be absorbed into the large merged galaxy or continue orbiting it as satellites. So, in the distant future, perhaps 100 billion years from now or more, the local group will no longer be a group of many galaxies. It will be just one or two giant galaxies, the product of many mergers surrounded by some very small dwarf galaxies. And that will be all that's visible. Imagine an intelligent civilization developing in that merged galaxy 100 billion years from now. They look up at their night sky. They develop telescopes. They begin exploring the universe. And what will they see? They'll see stars in their own galaxy, trillions of stars, if it's the product of the Milky Way and Andromeda merger. They'll see some small satellite galaxies orbiting their galaxy. But when they look outward into deep space, they'll see nothing else. The sky will be dark and empty. No distant galaxies. No galaxy clusters. No huge structures of the cosmic web. They might conclude their galaxy is the only one in the universe, that there's nothing else out there except empty space extending forever, and they'd be wrong. But how could they know? All evidence of other galaxies would have disappeared. Light from them never arrives. The CMB, cosmic microwave background, would have been stretched to the point of being undetectable. They'd have no way to know the universe was once vaster, fuller of galaxies. They wouldn't know about the Big Bang, about the universe's expansion, about the 100 billion year history that led to their galaxy. That's a profound and somewhat sad reflection. Knowledge of the universe depends on when you live. A civilization born too late might never discover fundamental truths about the universe's origin and structure because the evidence has disappeared. And that makes the present moment special. We're living in what some cosmologists call the golden age of cosmic observation. We live late enough to have sophisticated technology, powerful telescopes, space satellites, computers to analyze enormous data. We can observe galaxies billions of light years away. We can detect cosmic microwave background radiation from the early universe. We can detect gravitational waves from merging black holes. But we also live early enough that the universe still shows us its history. Distant galaxies haven't yet disappeared from view. The CMB is still detectable. The cosmic web structure can still be mapped. If we were born a trillion years later, we might never know about the Big Bang. We might never understand the universe is expanding. We might think our galaxy is all that exists. But we're here now, in a window of time when the universe is still telling us its story. And we're lucky enough, or perhaps more accurately curious and persistent enough, to listen. That's an extraordinary privilege. And it reminds us that nothing lasts forever, including the ability to see and understand the universe. But let's go even further into the future. Not just 100 billion years, but thousands of trillions of years. In the final merged galaxy, stars will continue being born and dying, but at an ever-slowing rate. Gas for making new stars gradually depletes. Each stellar generation enriches gas with heavy elements, but also locks part of the mass into dead stellar remnants, white dwarfs, neutron stars, black holes, that can't be recycled to make new stars. After thousands of trillions of years, star formation will slow to nearly stopping. No more gas, The last stars born will be tiny red dwarfs, living slowly, possibly existing for thousands of trillions more years. But eventually, even these red dwarfs will exhaust their fuel and die, becoming cold, white dwarfs, then black dwarfs, completely cold, stellar remnants, emitting no light. The galaxy will contain mainly dead stellar remnants, white dwarfs, neutron stars, black holes, all cold, dark, drifting in space, and the surrounding universe will be emptier and darker. No other galaxies to see. The CMB has been stretched to the point where its temperature is near absolute zero. No light sources, except perhaps a few remaining aging red dwarfs. That's the vision of the universe in the distant future. A dark, cold place where almost nothing happens. A universe that has passed its golden age and is slowly sinking into cold death. But even in that bleak vision, there's a strange kind of beauty. It's a beauty of stillness, of final peace. A universe no longer torn apart by supernova explosions, no longer brilliantly lit by newly born stars, just cold remnants drifting in darkness, carrying memories of the time when everything was vibrant. And perhaps, in that infinitely distant future, matter will find new ways to organize itself. Perhaps there will be processes we haven't yet imagined, phenomena that only occur in an old, cold universe. Or perhaps not. Perhaps that's truly the end. A dead, dark, and empty universe, extending forever. We don't know for certain, and fortunately, we don't need to worry about it. Those times lie so far away, they're beyond our imagination's capacity. What matters is right now, this very moment. We're living in a vibrant universe, full of light, full of structure, full of beauty. A universe where galaxies are still merging, stars are still being born, planets are still forming, and life can still thrive. We're living in the golden age, and that's both a privilege and a responsibility. A privilege because we can see the universe in its glory, can explore its history, can marvel at its scale and complexity. And a responsibility because we have the ability to understand, the ability to record, the ability to transmit that knowledge to future generations who will also live in this golden age before the window closes and the universe becomes dim and incomprehensible. And now, we've traveled a long journey through galaxies. Each galaxy is a story about time, billions of years of formation, evolution, change, a story about collisions, violent encounters creating new beauty, a story about light and darkness, brilliant stars and invisible dark matter, both necessary, both shaping structure.